Hello students. Today we will discuss on the last part of the plate guarded design, the design of stiffener. So to start with the design of stiffener, I will refer to a previous portion of our design where we have checked the D by TW ratio of the wave, where we have found it is greater than 67 epsilon. Well, as per the provision of our IS 800, we may say that shear buckling will occur, and to resist this shear buckling, we are going to provide the stiffeners. We have two types of stiffener: bearing stiffener and intermediate stiffener. Bearing stiffener are those which is provided just above the support. First of all, we have to check whether the bearing stiffener is required or not. That is, if the wave itself is capable to take the bearing pressure, it is not needed to provide the bearing stiffener. So here we can see, as per clause 8.7.4 IS 456 IS 800 page 67, here this bearing stiffener should be provided for wave where force applied through a flange by load or reaction exceeds the local capacity of the wave, and it is its connection to the flange. Fw is given by this. So this formula B1 is steep bearing length, and N2 is the length obtained by dispersion of the flange to the wave junction at a slope of 1:2.5 to the plane of the flange. So as we are testing the thing for first of all, to by not providing the stiffener, we will take for the first turn B1 is equals to 0, and N2 is found to be 125. How it is found? That here we can see the wave to flange junction, and here we can see the thickness of the flange we have already calculated as 25 millimeter thickness. So if it goes to 1:2.5 ratio of dispersion angle, so it will have a length of 2.5 millimeter, and here 2.5 into 25 millimeters, so it will be 125 in considering two sides. So N2 is considered as 125. Now TW is 10, FYW is 250, and 1.1 we have got it as 284.09 kilonewton, which is less than Vmax, that is 465 kilonewton. It shows that the stiffener is not capable to take up the bearing pressure without the provision of bearing stiffener. So bearing stiffener is required is our assertance here. Now we'll check the compression of the stiffener. So in figure 1, here we must see that we have to consider the core of section. Here also in our code we have the provisions. As per clause 8.7.1.5 page 66, we can see the clause. Let us read the clause. The buckling resistance FQD should be based on the design compressive stress FCD on the strut of curve C. That they have said that we have to consider this bearing stiffener as a strut along with the core area. So, and this should be considered as buckling class C, where the core area has been referred. So the radius of gyration being taken about the axis parallel to wave, the effective section is full area or core area of the stiffener together with the effective length of the wave on each side of the central line of the stiffener, limited to 20 times the wave thickness. The design strength should be minimum the value obtained by buckling about the wave stiffener. So as we have shown here, we have to consider 20 times of the wave thickness in the either side. This portion of the wave along with the wave stiffener will act as a core of the section. This will comprehensively act as a strut in this case. So what we have done, first of all, for checking the stiffness, I am referring figure 1, what we have considered, we have calculated the core of the area of the section, for which first of all we have to find out the projection here. So according to the code, we have to find out the projected area. We will see there is a provision here 8.7.1.2 outstand of the wave 65 page. Outstand means this portion, that is the portion which is projected beyond this wave portion. Or if you go to this picture, this portion, this is projected one, how much projection or outstand will be there? They have said that unless otherwise edge is continuously stiffened, the outstand of the face of the wave should not exceed 20 TQ epsilon, where the outstand of the wave being 14 and 20 TQ, then the stiffener will be designed. Stiffener design should be on the basis of core of section with an outstand of 14 TQ epsilon, where TQ is the thickness of the stiffener. So what we have done here in the example problem, we have considered the thickness, that is TQ, as 10 millimeter. So the outstand is coming as L0 is coming as 140 millimeter, and so the area will be 2 into 140 into 10. There's two stiffeners, and 2 into 20 TW into 10, 20 TW is coming as 200. For either side it will come as 400. So the area is 6800 millimeter square. Now to find out the compression capacity, first of all we have to find out the core area in moment of inertia value. So what we have done, we have calculated the moment of inertia. About this axis they have mentioned already that we have to consider the longitudinal axis of the wave. In the code this provision was given, so it will be the BD cube by 12 of this wave portion, 400 into 10 cube divided by 12, and the BD cube by 12 plus parallel axis transfer of this stiffener portion, that will be B will be 10, and D is 140 cube divided by 12. And what should be the distance between the CGs is, this distance is at 70 from this face, and half of the 10 will be 5, so it will be 75. So it will be 140 into 10 into 75 square. So the moment of inertia is coming as 20.36 10 to the power 6 millimeter to the power 4. So to find out the R minimum, the minimum radius of gyration, we have to find out root over I by A. This is I, and we have calculated already the A. So I by A is coming as 54.72. Now we have to find out the slenderness ratio KL by I. Now what should be the value of K is given in code. Here we can see just below this clause at page 66, it is mentioned that the effective length of the intermediate transverse stiffener used in calculating buckling resistance FQ should be 0.7 times of the L, and also for the bearing stiffener it is considered for 0.7 into L. So we have considered here the effective length as 0.L divided by R is coming as 12.79. So we have referred the clause here, and they have said that you have to consider it as buckling class C. So the table 9C has been considered, which is in page 62 of IS 800, and from where we can calculate the value of FCD if we know the grade of steel. Grade of steel is given as Fe 410. So the buckling yielding yield stress Fy will be 250. So FC will be I core into FCD. This is the area of the core, and this is the FCD. It's coming as 1537.9, is less than Vmax. Hence, it is safe. This is the simple detail that I have provided for your reference. The center to center distance is 1 meter. We have said that C will be equals to D, and this is the cross section where we have to mention all the dimensions clearly. So with this, the design of plate girder ends. Thank you.